Hi everybody, welcome back. This is Unit 9, Lesson 3, and we're going to talk today about factors that can affect the solubility of a solute. So how well a solute dissolves in a solvent. I know you probably are familiar with some. We did a demonstration earlier this week or last week where we talked about polarity. And that polarity is really the overriding factor. Remember, we made our red, clear, and blue flask with our water, our oil, and our alcohol. So the major determining factor in whether or not something dissolves is its polarity. Okay? What we mean on the notes where we say the nature of the solute and solvent, we're referring to the polarity of those substances. And what we learned is that polar solutes, like NH3, dissolve in, I'm on the second dot now, polar solvents. Can you think of any polar solvents? Probably the most common solvent that you know, right, is polar water. Water is a polar solvent. If it's polar, it has partial charges, and it's able to pull away the partial charges on the polar solute. So polar things like NH3, or even remember our alcohol, those dissolved in water because water is polar. Non-polar solutes like carbon dioxide and methane gas dissolve in non-polar solvents. Probably the most common non-polar solvent is carbon tetrachloride. They use that a lot in the dry cleaning industry, because it'll get out oil and dirt and grease and other things. Oil is also nonpolar, dirt, grease, those are all nonpolar things. And so it really doesn't do any good to put water on oil because water will not be able to get it out. But if you use carbon tetrachloride, you'd be able to get it out. And then ionic things, right? The metals bonded to the nonmetals, we call those salts. They will dissolve in, obviously you've made salt water before, so they dissolve in polar solvents as well, like water. So in describing this, we use the phrase like dissolves like. And again, what we mean is that polar solutes dissolve in polar solvents and non-polar solutes dissolve in non-polar solvents. Okay? So with that being said, this guy is asking this other guy, what kind of bear dissolves in water? And if you understood the last section of notes, you should be able to answer that question. A polar bear. Because water is polar and the bear is polar, so he will dissolve in the water. And for those of you that don't get this, this is really only a joke. Polar bears are really good swimmers. They don't really dissolve in water. It's just a joke to help you remember that water is polar. Temperature also affects the solubility of solutes. And probably you are familiar with the idea that cocoa mix dissolves better in hot water than it does cold water. Sugar dissolves better in hot water than it does cold water. Even coffee creamer dissolves better in hot water than it does cold water. So for most solids, the hotter it is, the better they dissolve. As temperature increases, the solubility of most solids also increases. Remember, solubility is just the ability to dissolve. However, for gases, it's opposite, and this is super important. Gases are not more soluble in hot water. They are less soluble in hot water. As the solubility, or as the temperature of a solution increases, the solubility of the gas will actually decrease. So you can dissolve more gas in cold water, like oxygen gas, like for fish, than you can in hot water. Okay? Same thing with carbon dioxide as well. You can see here, this is the solubility curve over here for a gas. And compared to the solubility curves in table J or table G, you notice that these ones go down. So the higher the temperature, the lower the solubility. Very important concept that you recognize. Solid curves would look like this. This would be a solid. Okay? As it gets hotter, you dissolve more. But gas curves, as you can see, go down. The hotter it is, the less you can dissolve. Okay? That's a very important concept with global warming. If our oceans warm too much or our bodies of water warm too much, then there won't be enough oxygen dissolved in the water to support aquatic life. So I know based on the winter we've had, many of you don't believe that global warming exists, but they actually attribute the rough winter that we've had to global warming, because one of the ideas with global warming is that you get extreme temperature changes and extreme weather patterns. And I would think that we all would agree that what we've seen this winter is definitely an extreme winter pattern. My son was super excited this morning because the thermometer on the car read in the double digits for 3 days in a row. 3 days in a row. Okay? Pressure is the final factor that affects solubility. Again, we're talking how much dissolves rather than how quickly something dissolves. We'll talk about speed in another chapter. So really just how much of it can dissolve. And pressure does not affect the solubility of a solid or a liquid. Pressure only affects the solubility of gases. And you need to know what the relationship is between pressure and solubility. The higher the pressure, the greater the solubility of gas molecules. Okay? The lower the pressure, the less soluble gas molecules are. And that's what this diagram over here is showing you. So in the first picture, there is low pressure, and you notice that much of the gas is above. There's very little gas dissolved, okay? In fact, there's no gas dissolved. But when you increase the pressure, that's what you're doing here. This is high pressure, right? You push that syringe down, you force those gas molecules into solution. So all of these are now the gas molecules that are dissolved due to the increase in pressure. Okay? And that's why when you think about soda pop, soda that you drink, soda has carbon dioxide dissolved in it. Okay? When you before you open a soda pop, if you ever felt it, it's super hard. The bottle is hard and rigid. You can't really squeeze it. And the reason for that is that the pressure is high. Soda is bottled under high pressure. Because what you're really doing when you make soda is you're carbonating it, right? You have your pop here, and you're pushing carbon dioxide down into the liquid. And carbon dioxide doesn't want to be in water. It's nonpolar. So you have to bottle it under high pressure. And then when you open it up and you take the lid off, so now pretend it's open, and you take the lid off, you hear that whoosh, right? That whoosh is all the carbon dioxide that you forced in under high pressure out. So when you release the pressure and lower the pressure, the carbon dioxide comes out of solution. And then if you put the lid back on, remember it's never as rigid as what it was because it's not under high pressure. There's not as much carbon dioxide dissolved. So gases are more soluble, and this is the bottom line. Gases are more soluble, or are most soluble, and I think it's one of the things you write in your chart every other week, when temp is low and pressure is high. That's when your gas will stay dissolved in solution, and that's when your pop will stay the fizziest. So you want to keep it cold, and you want to keep the lid on your soda because that will keep the carbon dioxide dissolved. You take the lid off, you warm it up, your carbon dioxide comes out, and your soda will go flat fast. Have a great night, everybody. We'll see you in class tomorrow. Bye-bye.